Yeah. Let's see here. Make sure the pointer's working. Yeah. Okay, questions? What we got going so far? Yeah.
I wanted to ask if anybody else wanted to push the homework back.
Am I supposed to push the homework back? Okay, I'll go ahead and put it back to, I'll go ahead and put it back to next Monday. Don't pretend that it's due tomorrow. Okay. Okay, okay. Yeah, I can give a little more time. Like pretend it's due tomorrow, but the whole, you know, if you've been working at it, then I have no problem kind of giving a couple extra days if you're, you know, working hard at it. Let's see here. I'm just doing this right now because if I don't do it right now, then my battery power is going to run low and then I'll forget something later. And okay, so we're doing the electric field stuff. Let's edit the settings and timing. We'll set it for the 8. Okay, there you go. Like I said, pretend it's due tomorrow or Tuesday. So there you go. Now, I feel like Doc Brown sometimes, right? Oh! No? Yeah, I love that one scene where like jams the chord in and then it comes undone down at the bottom, and his scream there is just great.
I remember this one kid sent me. It was about like, there's something about like whenever you try to improve your grades, and the old like Pokemon cartoon where like Charizard has a little like watering can and his tail sets something on fire and then he turns around and it just loops over and over.
Oh.
You're trying to put the fire out. It feels so sad. Because I want to see it.
You'll have to send it to me.
I can't remember.
Don't do it right now. I mean, I'm just impressed that I know who Charizard is because Graham took up Pokemon like last year or something. So I'm like, oh, I know who that is now.
Like when I was 12,
Mhm.
still want to see stuff.
Yeah. Okay, so that's taken care of. Other questions? Yeah. I'm sorry?
Like on the final problem with the electrical field, what are you asking?
Remind me, what's the final problem on the homework?
Like make a graph X with some symbol that I don't know at all. 4A, A4A.
Oh, okay. I gotcha. Okay. Yeah. So the final problem in the homework is something along, sorry, I don't have like a blank, do I have a blank spot here? Yeah, let me do it this way. Sorry, rather than just trying to draw it on the screen there, we'll just do this. So I think now that'll put in an extra blank page for me. Okay. So the final problem on the homework is something like this. Where in the world? There it is. So you have an x-axis, something like this, and you have two charges, if I recall correctly. And I think it's a dipole, right? They're same magnitude, just opposite signs. So I call one positive Q. I think I call one positive Q and I call one negative Q. Okay. And I don't even remember if I put them equidistant, but let's just run the y-axis between the two. Yeah. Oh, and I put them a distance a away from the y-axis, don't I?
Yeah.
Okay, gotcha. So this distance is a. Now I don't care what a is. It could be 1, it could be 2. It's just some generic distance. And then the problem asks two things, if I recall correctly. One thing it asks is it says, hey, for a given location in space, find the electric field. Right. For a given location in space, find the electric field, except I think it goes, maybe I shouldn't say a given location, it said find the generic expression. right? So it doesn't matter where I am on this x-axis, find a generic expression that would tell me what the electric field is. I think that you're gonna have to break it up into 3 segments. So you probably need to find an expression for the electric field if you're over here on the right-hand side. You'll probably have to find an expression if you're in the middle, and I think you'll have to find an expression for the left-hand side. So you might have to think about that as 3 separate cases, which actually only ends up being 2, because, I mean, I gave you 3 separate spots, but I think it'll only end up being 2. Why?
It's the one on the far left and right, same.
I think the one on the far left and the one on the far right are gonna look the same, or at least be very similar. Okay, yeah. So that's the general idea, is find what general expression for the electric field on the far left, the middle, and the far right. And the last piece is, I tell you, plot the, oh, okay, I gotcha. Then it says, hey, plot. So create a plot for X. I had something like this, didn't I?
Yeah.
Okay, I know exactly what it is. Okay, sorry. Yeah, how do I explain that? Oh, yeah, okay. So what this means, starting at a distance of -4a, so that's telling you how far on the left-hand side, make a plot, and go all the way until you're at a distance of 4a on the right-hand side. Okay. So what this means is, for all points contained between -4 and 4. Okay. So this fancy E symbol is contained in this interval. So sorry, that's my math major coming in. It's just a shorthand for values of X between -4a and +4a. Yep.
So whenever you plot, you might graph the distances on a different separate graph, or how do you?
Yeah, what I think what would be nice to see is, we'll say, the electric field as a function of X. Yep, good. Yeah, and I'll say right at, let's see. Yeah, the electric field is a function of position. And it doesn't have to be, you could probably just, you could make something in Excel and just do a scatter plot, and that would probably be good enough. So it doesn't have to be a continuous line. You could just say, okay, well, let's do it at 4a, and do it at 100 points between -4a and +4a, and plot it. That should be fine.
What does it mean, plot?
I'm sorry?
What does it mean by plot?
Yeah. Create a graph of the electric field as a position of X. So you'll have some expression for the electric field, and I just want you to visualize. I just want to see it, see you plot it, just visualize it. And I hazard to guess that you'll probably have some places where the electric field is 0. No, it's a dipole. Never mind. You won't have a place where the electric field is 0.
Well, we're on the y-axis.
Oh, I just said one-dimensional. So you're just considering stuff on the x-axis.
So you would just make up a number for A?
Yeah, for plotting purposes, you'll have to make up a number for A. You'll have to make up a number for Q. Yeah. And in fact, I would encourage you, really, I'm interested in what the function looks like. I would encourage you, here's a really good value for Q, 1 nanocoulomb. Why? Just out of curiosity. Why would 1 nanocoulomb be of probably a convenient value for Q?
Is your number stored
Easier numbers to work with. Why would 1 nanocoulomb make the electric field an easier number to work with?
Because A is.
Yeah, you remember the expression for the electric field. I guess I'll go up here. The expression for the electric field is KQ over R squared. This K, the Coulomb constant, is on the order of 10 to the negative 9th. Excuse me, 10 to the positive 9th. Oops. Where's my eraser? 10 to the 9th. So if you choose a nanocoulomb as your source charge, that's 10 to the negative 9th. And that'll make those two numbers cancel out, and then hopefully your numbers will be like some reasonable value. Yeah. Now you didn't have to do that. You could say 1 coulomb, and then your electric field is going to be on the order of 10 to the 9th newtons per coulomb. It'll make the scaling really goofy. But yeah, go ahead and do like a nanocoulomb. No, that'll just make the numbers at least reasonable. Yeah. Other questions?
This is a bar charge, and then effect on the one, the function opposite side of it. So,
Question for you. Does the electric field obey superposition?
I don't know.
Yeah. What say the rest of you? Does the electric field obey the principle of superposition? Survey says yes. So the answer is yes.
I don't remember what that will have this.
Oh, the net field is given by the contribution of the individual pieces. Yeah. So the superposition basically says if you want to calculate the net force, you do the individual forces and add them together. So if you want the net electric field, you do the individual electric fields and then add them together. So yes. So yeah, the negative Q over here will still contribute to the value of the electric field over in this region.
So how far does that region go, or is it just?
Well, when you're plotting, I say go 4 times the distance. So yeah. And that I think that's going to be far enough away. You'll see that you'll essentially have 0. It'll be a really, really small number, but then as you get closer and closer to the dipole, you'll see the electric field get really large.
Do we need to plug in any value for A?
You'll have to choose some values for the charge and for the A. Yeah. I mean, if you really get jazzed, I mean, if you're going to do it in like Excel, then yeah, you'll have to choose some values for the charge and for the distance A. If you're familiar with, like MATLAB, or if you've got some programming experience in Python, you could plot something more sophisticated where instead of doing a scatter plot, you could do a function plot, and then you don't have to specify, it'll just plot the functional dependence for you. If that means nothing to you, don't worry about it. But I just thought, oh yeah, it's kind of a cute exercise of just plotting stuff. So. MATLAB, I mean, I don't know if you guys use, what kind of software programs do you use? I'm just curious. Python? Okay, Java?
We're using MATLAB instead.
Okay, yeah, so MATLAB has a lot of plotting features, so you can use MATLAB to plot it instead if you wanted. If you want some practice, and my guess is Stats will probably have you use some plotting.
Or do we just throw it out?
Well, no. I want you to at least do it with a computer. Yeah. Yeah, back in the day, yes. What you'd have to do is rip off the graphing paper and actually put the tick marks in and plot it like, manually. But yeah, nowadays, people look, if you handed in a hand-drawn plot, people are going to look at you a little weird. Here's my answer. I got it. So, sorry, you guys are too young to take advantage of the hand-drawn plot era. So you're going to have to do more sophisticated now. Sorry. But look on the bright side. You guys never had to know the pain of somebody having 4 zeros in their phone number? That makes no sense to you, does it? Yeah. Before your digital phones, there was what's called a rotary dial phone. Okay. So to type in a number, you had to, I mean, it was, there was numbers around a circle. You basically had to spin the dial, and then you let go and the dial would spin back, and then you have to spin the dial again for the next number. Okay. Now the problem is that it goes 1 was the short one, and then 2, 3, 4, 5, 6, and it went all the way around. 0 is the very last one. So if you wanted to call somebody that had zeros in their number, you had to spin the dial almost all the way around, let it go back and go. Then you had to do it again, and let up and it go. It would take you like a minute just to dial the phone number. You seen those rotary dial phones? Like, okay, yeah. So you prayed that there weren't zeros in the number because it would take forever to actually dial it. Nowadays, you just hit a button and it dials 0, but yeah. So you see, there's a trade-off. You guys will also never know the pain of somebody sticking an index card in the wrong spot. Because like when you went to the library and wanted to find a book, you couldn't look it up on a computer, right? Nowadays, you just type in the title of the book, it spits out the call number, and you just go. Right? Back in the day, it was what's called a card catalog. You pull out a drawer, and there could be 1,000 index cards, and you had to page through and manually find the book you're looking for. And it was alphabetized, either by title or by author. I can't remember. It was by author, I think. So it was alphabetized, and you pull it out, and you have to look for the author's name and pull out the index card and get the call number, put the index card back, and go and find your book. Right? The pain was when somebody didn't put the index card back where it belonged. Because it's supposed to be alphabetized by author name. You're looking for the author name and they put it in the wrong slot. Or heaven forbid, you pull the whole drawer out and then the index cards fall on the floor. But that's the worst. Like you hear somebody do that, you just leave the library because the librarians are screaming. Like, no? Okay, let's get back on topic. Sorry. Okay. Other questions? You guys, right? You take a family photograph and not know if it's a good one for 2 weeks, by which time you see your little brother's like there, like this, eyes closed. You're like, well, I guess that's going on the Christmas card because that's the only one we have. No? Okay. Okay. Yeah, okay. I said last time, I think on Friday, I said, hey, yeah, go back and look up this idea of conservative forces. Refresh your memory about what does it mean for a force to be conservative? What can you tell me about the work that's done by that force? Which forces do you know of that are conservative? Just to kind of prime the pump and, bank on your memory, that kind of thing. So yeah, I mean, what does it mean for a force to be conservative? Or what can you tell me about work done by a conservative force? What do you remember about conservative forces? Do you remember talking about conservative?
Did the call drop?
This is starting really to peeve me off here. How long? Okay, I hope I wasn't gone too long. Sorry, this apparently dropped on me again. Am I still recording?
Yeah, you were gone for like 10 minutes.
I'm sorry?
You were gone for like 10 minutes.
Shoot. Okay. We're back. Okay. They missed the card catalog discussion. They missed out. Okay. Yeah. Okay. So the linear path and the loopy path, the work done by those two like traveling those two paths is they're equal. Thus is the idea about conservative forces. Okay. The issue is, you could say, well, how are they going to be equal? You notice that, okay, yes, during this loopy path, the force is going down, the path is going off to the side, and so you get some cosine angle in there. Okay. But it turns out that as you go around this loopy path, if you take all of those little segments and add them all together, you end up with the exact same work. In other words, the path that you travel doesn't matter. You can approximate the loopy path as being a straight line. For the purposes of determining the work, that loopy path and the straight line path are exactly the same. And that is a general idea with conservative forces. A conservative force, if you want to calculate the work done by a conservative force, the path doesn't matter. We say it's path independent. I could go, I mean, I drew the loopy path, but I could have just as easily said, well, I'm going to take a path where I go all the way down and maybe I come over here, I go around the world a couple times, and then I come back to this final position. Regardless of how ugly that path looks, the work is the same as the other two paths I previously had drawn. Because it's independent. The only thing that matters is where I started and where I ended. You can think of this in your daily life. So you're on the ground floor of the science center. Maybe later you go up to the third floor to geology, and then you drop down to the second floor for biology. Then you realize you left your water bottle in the geo lab, and so you go back up to the third floor, and eventually you go to exit the building on the first floor. How much work was done by the gravitational force, starting on the first floor, going to the third, down to the second, back up to the third, and back down to the ground? How much work was done? None. Because you started off on the ground floor and you ended up on the ground floor. The only thing that matters is where you start and where you end up. It doesn't matter in between what goes on. Same thing mountain hiking. Right? It doesn't matter what path you travel, you start, I mean, like at the end of the day, you're back at the original spot and it's zero. Good so far? Quick, can you name some conservative forces? Can you think of other forces that are conservative aside from, we'll say, the gravitational force? And you got to go through and say, okay, well, what other forces have we dealt with before? Which ones sound, which ones do I remember? Here it is. Quick, what other forces have you talked about? Forget about if they're conservative or not. Just what other forces can you think of? Frictional force. Let's think about that for the good. Let's say I have point A on one side of the desk. I have point B on the other side of the desk. And I slide a mouse between those 2 points. Straight line. You can think of, well, we're not going to go through and calculate it because you need a lot more information here. But you could think about, okay, there's some work associated with that. If I push the mouse, say I slide it, right, I give it a go and it goes all the way across. Right? You can think there's some work that the frictional force has done on the mouse, going from one side to the other. Now, if I take a different path instead of a straight line path, let's say that the mouse somehow, slides all the way out to the end of the room and slides back and kind of does like a little wavy thing and then ends up here. Are those two works going to be the same? Intuitively, what do you think? No. The frictional force, the work done by the frictional force is going to be larger for the longer path. For this case, the frictional force is larger for the longer path. The frictional force is a non-conservative force. The path that the object takes going from point A to point B matters. Right? The straight line path ends up with a different amount of work done than if I do a curly-Q pattern somewhere. So the frictional force is a non-conservative force. One that's pretty close to that I kind of think of as the same way, air drag. Air resistance is a non-conservative force. You can imagine if your car drives in a straight line from, say, Hanover College to Gendes, as versus if the car goes out the north entrance, goes over to Madison, then drives back to Gendes. In the second case, the force of air resistance has done a lot more work on your car. It's a non-conservative force. It doesn't depend on A and B. It depends on the path you take between them. So friction, and I feel like friction and air resistance kind of feel the same there in terms of that. What other forces have you dealt with? Tension force. Yeah. That's a really good one. Oh, shoot. That one's gonna, is that one gonna depend? I think that one's gonna depend on the situation. Nuts, you caught me. Yeah. Because the thing I'm thinking about, do we actually have a specific equation to define the tension force? Can I say, anytime you have the tension force, here's the equation you write? Survey says, no. In fact, generally when you have the tension force, how you find the value of the tension force is you account for all the other forces and then you can use that to find the tension force. Yeah, so the tension force is very situational dependent. So we don't have an equation for that. So sometimes it could be conservative depending on the situation. And other times it would be non-conservative depending on the situation. Say I'm dragging the car from Hanover to Gendes. Right, now the tension force is going to be related to the force of air resistance, and then I'm in, yeah. But if I'm lifting something against the force of gravity, then maybe it's conservative force. So it's situational dependent. Yeah. Good. Springs? Do you deal with Hooke's law or the spring force law? I'm seeing some nodding. What do you think, conservative or non-conservative? Conservative. If I take a spring and I stretch it, say starting point, ending point, there's some work that's been done there. But if I take that spring and I stretch it and then I de-stretch it and then I stretch it again and then I put it at the end point, it's the exact same as if I just stretched it right away. Right? Yeah, so the spring force is conservative. Yep. Other ones?
Force between charges.
The force between charges. We said that gravity is conservative. Now, I did it for gravity close to the surface of the Earth. But the question would say, hey, what about if we're dealing with large distances? In other words, I can't use my close Earth approximation. What happens if I have to use Newton's, full-blown version? So G m1 m2 over r squared. What happens if I have to use that? Survey says it still only depends on where you start and where you end. And because universal gravity is a conservative force, And gee, Coulomb's law looks a lot like universal gravity. Maybe Coulomb's law is also a conservative force. Indeed, the Coulomb force is a conservative force as well. It doesn't depend on, the force between charges. It doesn't depend, say I have my source charge, I have my, like I'm moving this one back and forth. It doesn't depend on the path that I take moving the charge from A to B. Right, I can just squiggly line it, or I can do it straight. Either way, the same amount of work has been done. Yeah, so absolutely, which is, of course, why I even bother talking about this. Right, if Coulomb's law were a non-conservative force, then I wouldn't even bother going through that discussion. Is it okay so far? You kind of jogging, is this jogging your memory a little bit? Yeah. Yeah. So, okay, yeah. So why bother going through all of this? Conservative forces have a very special relationship between forces and work. Or, I guess a different way I could say it is that conservative forces have a very special relationship between the force and the potential energy. I'll say that again. There's a very special relationship between the force and the potential energy. You okay with work, instead of saying work, potential energy? So usually I'll let you know how I'm thinking of it, and if you agree with me, great. If you disagree with me, that's okay. Find a way that kind of makes sense to you. Okay. But how I think of this is, say I have a ball. I have a ball and I have the earth. Okay. I have, sorry, that's a really bad earth, but that's a really bad spelling of earth. Well, it's a good spelling, it's a terrible writing of earth. I have a couple of choices here. How I could think about this is I could think of the earth as being in the surroundings and exerting a force on the ball. And in that case, that force of the earth on the ball exerts, it does work. An external force does work on my system. The other way I could think about it, because I am free to choose, okay, I could put the earth and the ball into my system. I could consider those both as being part of my system. And so now, rather than thinking about forces, because a system can't exert a force on itself, right? Unfortunately, I can't hop in my car and push my car. I can't hop in my car and then push myself in my car. That would be pretty cool. Right? That's not allowed. I can't, as the system, I can't exert a net force on myself. So one way is put the earth in the surroundings, that you talk about forces that the surroundings exert on your system. The second way is to conceptually keep the ball and the earth in the system. And I can't talk about forces anymore. But what I can talk about is energy, change in potential energy. So in my mind, how I think of the difference between work and potential energy is simply, did I decide to put the earth in my surroundings and then I have to talk about work, or did I put it in my system and then I talk about potential energy? So that's why I kind of flipped from work and go into potential energy. It's a conceptualization. Which do I include in my system? Is that okay? You'll find yourself making that conceptualization, switching back and forth of what's in your system and your surroundings. I know that comes in a lot in thermal. So get used to thinking about system and surroundings if you're planning on taking thermal. Not physics thermal, I mean even chemistry thermal. Okay, so So I said, yes, there's a very specific relationship between a conservative force and a change in potential energy. And in fact, I'm just going to go way off script and put another slide in here. This is what I'm going to do. Way off script. There we go. Make sure that my Teams people, yep, we're still here. Way off script. So let me throw this in. Or, oh, good gravy. Please tell me I didn't just kill Microsoft. Aw, man, you know, sometimes I wonder about this technology thing. You know, what we should do is we should put whiteboards and, no, I'm sorry, chalkboards. Because whiteboards don't always erase, right? Chalkboards, you always know they're going to erase. There we go, okay. Oops. So I'm going to go off script here, but yeah. Here's a question for you. So what I'm going to do, let's think about what would this relationship actually be. And what I'm going to do, if I can get my little pointer back, there we go. Let's just do a little plot here for a second. I will call this distance for sake of argument, I'll call this x. And on the y-axis, do you want to think about height or do you want to think about gravitational potential energy? Do you have a preference? I will call it height for a second. So I'll call it height. Height. But bear in mind, the gravitational potential energy is simply mgh. So bear in mind that if I'm thinking about height, you could similarly say the shape of the graph for gravitational potential energy is going to look the same. The only thing that changes is the scaling on the y-axis. Instead of it being like 1 meter or 2 meters or 3 meters, it'll be, 10 joules, 20 joules, 30 joules, something like that. So it's not going to change the shape, it only changes the scaling, the tick marks on the y-axis. Okay. So let's pretend here for a second that I've got a graph, and I'll just do this as 1D. So I've got a graph of height versus position, and yeah, I'll do it something like this. Straight line going down, and we'll just take it to the ground. There we go. Now imagine for a second, this is a 1D graph, but imagine for a second that we placed a ball on the side of this graph. Say right here. First question for you. Which direction is the ball going to roll? If I had a 1D graph and I put the ball on the side, or a 1D hill, I guess, and I put the ball on the side, which direction is it going to roll? Not a trick question. I'm just... It's going to roll down. Is it going to roll in the x direction? Or is it going to roll in the negative x direction? X. Yeah. You have the right idea. Yeah. It's going to roll in the x direction, right? If I put it here, it would roll, down the hill. I'd say it would roll in the positive x direction. Good. So it's going to roll in the positive x direction. Second question then, if it goes in the positive x direction, what direction is the force acting on the ball? Keep in mind, this is just a 1D, I'm thinking of 1D for right now.
It's the same way.
It's gonna, I'm sorry?
It's just the same way.
Same.
The ball's going.
The same way the ball is going. Yeah. I have rescinded my previous thought. Forget about this as being height. Think of this as gravitational potential energy. I realize if I think of this as height, you're thinking of a two-dimensional process of a ball physically rolling down a hill. Okay, and then you're saying, okay, it changes in the x direction and the y direction. I don't want you to be thinking about 2D right now. I just want 1D. So I apologize. I'm going to rescind my previous thought. Think about this as being a gravitational potential energy versus position. And if the position of if the ball is rolling in the x direction, positive x direction, which direction does the force have to be acting on the ball? If it's accelerating in the x direction. Has to be in the x direction. Is that okay so far? So ball is moving in the positive x direction. The force must be directed in the positive x direction. All right? Yeah. Next question. Let's say I do the exact same plot, except say x and potential energy, U, G, except now it's like this. Whoop. There we go. And I put a ball, you could conceptualize having a ball on the side of the hill. Which way is the ball going to roll? The negative x direction. So which way is the force acting on the ball? If the ball rolls in the negative x direction, to the left, it'll be in the force will also be in the negative x direction. So top graph, ball rolls in the x direction, and the force is in the positive x direction. Bottom graph, forces, or the ball rolls in the negative x direction, the force is in the negative x direction. Okay. Question. Top graph. What can you tell me about the slope? Positive or negative? Negative. A negative slope results in a force in the positive direction. Bottom graph. What's the slope? Positive or negative? Positive. A positive slope results in a force in the negative direction. Sorry, that might be a long way around to where I'm trying to go, but what I want to emphasize here is that there's a relationship between the slope of the potential energy graph and the direction that the force is. Could probably even go further than that. There's a relationship between the slope of the potential energy graph and the magnitude of the force. What say you? If the potential energy graph were steeper, is that going to indicate a stronger force or a weaker force? Stronger. You could think of it literally as if the hill is steeper and I put a ball on the side, will the ball accelerate faster or slower? If the hill is steeper. Survey says faster. If I don't make the slope very steep, the ball doesn't accelerate as much, and so the force must be lower. So there's two things here. This sine of the slope, okay, let's see. Sine of slope, and magnitude of slope. Sorry, I'm not looking at the screen, so hopefully this is okay. Ah! Wow, that's really off. Okay, excuse me, I'll just say it verbally and not write it down. So you have two things. You have the sine of the slope, and you have the magnitude of the slope. The force, whatever the sine of the slope is, the force is in the opposite direction. So if you have a positive slope, force is in the negative direction. You have a negative slope, force is in the positive direction. So it's always the opposite sign of the slope. And the magnitude of the slope indeed tells you the magnitude of the force. Now mathematically, just out of curiosity, how do we do a slope mathematically? How do we calculate a slope? If I said slope is equal to, how would I do a slope calculation? Just in general, for any kind of graph. Change in y over change in x. Change of the dependent variable over change in the independent variable. Or sometimes you'll see it, slope is rise over run. For this graph, The rise is change in potential energy. The run is change in position. Okay. So the change in potential energy over the change in position, I'll use X here. That will actually give you the magnitude, excuse me, that will give you the magnitude of the force. The steeper the slope, the stronger the force. The less steep the slope, the weaker the force. Which you guys have already used in this class last week. When did you use this in the class last week? You didn't use that equation, but you used that idea. We used that idea a lot last week. When were you looking at slopes to determine magnitudes?
The topographical map.
You remember doing the topographical maps? Right, what are these topographical maps actually? Okay, let's go back here. We'll find it somewhere. What are these topographical maps actually telling us? It's telling you elevation. You could think of, hey, instead of elevation, if you just multiply by mg, this topographical map is showing you potential energies. And the same thing applies. How do I know when I have a large force acting on an object? I drop a ball on the side of the hill. How do I know if it's a large force or not from the topographical map standpoint? Quick, how do I read a topographical map?
The lines are close together and then it's steeper.
Good, the lines represent constant elevation. When the lines are closer together, you have a steeper slope, a larger change in elevation for a distance. Or, if you prefer, a larger change in gravitational potential energy per distance. You have a larger change in gravitational potential energy for a distance. That is a larger force. I would argue you're using this idea when you're looking at the topographical maps. You just internalize it, like lines closer together, steeper slope, that means it's a greater force. The only piece that I'm introducing here is greater change in gravitational potential energy is a greater force. It's done silently. You guys okay? This sort of making sense? That's why I like topographical maps. That's why I like them, is because it just gives you a little bit. You're used to dealing with them in 5th grade. The only thing I'm doing is telling you the mathematical relationship now. The slope is related to the force. Steeper slope, stronger force. Less steep slope, weaker force. Yay, nay? Okay, now we gotta go through all the animations. There. Oh, I'll have to erase that one later. This relationship only applies for what kind of forces? Conservative. Remind yourself of that. This relationship only applies for conservative forces. So be careful about that. If I want to find the magnitude of the force from the potential energy, I have to ask myself, is this force conservative or not? If yes, good to go. Go for it. If no, proceed no further. shoot, I seem to remember some plot about bonding of electrons to the atom. Right, have you, the energy curve plot for an electron bound to an atom? I don't remember what it's called. Just, sorry, I'm going to speak to the chemist for a second. If I plot the position of an electron, this origin being the nucleus, and the potential energy, you end up with something like that. What is that graph called? I can't remember. I don't even. Yay, nay. Is this looking familiar? Okay, I'll look it up later then. Okay. Strike that from your memory banks. I'll look it up later. The question I was having is this if this is a conservative force, then you can just use the slope of the graph to find the force on the electron due to the proton or the nucleus. Incidentally, this isn't Coulomb's law because this also includes electron shielding, if I recall correctly. So it doesn't look like 1 over r squared. You have, if you get too close to the nucleus, then the inner orbitals of electrons will repel an outer electron. And if you get too far away, then they'll want to pull the electron back in. I'll have to look at that. I don't remember for sure exactly. Sun silence. Am I making that up, or does that sound about right? Yeah. Okay.
So for like topographical maps, since the two lines like are the same change in elevation per line,
Mm-hmm.
does that mean that between lines is the same change in gravitational potential?
Yeah, absolutely. Yeah. Yep.
They're only really changing the distance.
Yeah, you're changing the line spacing. Yeah. Mm-hmm. Yeah, that's one way to think about it. These lines are same elevations, and therefore, as long as I'm dealing with the same two lines, it's the same change in gravitational potential energy. Yep. It just depends if you're walking a steep slope downhill or you're walking a nice gradual slope. You know, are you going to bust a knee, or are you just going to, have a pleasant stroll? See if we can get this a little bit. Yeah. Did I have this organization slide last time? I can't remember for sure. There we go. Get that out of the way. So I thought organization. What we're really working on is I wanted to draw another link in here. So first of all, we have kind of given the Coulomb force, we can kind of get how to get the electric field. Namely, if I remove the system, the charge of the system, I can go from a Coulomb force over to the electric field. This side is describing the surroundings. Okay. I want the left side to describe the surroundings here. What I write over here on the right side is going to describe the interaction of the surroundings with your system. So if I want to talk about just the surroundings, I take out the charge of the system. If I want to talk about the interaction of the surroundings with a charge, then I have to multiply by that charge to get into the interactions. So that's all I mean by this upper one. If I have my force and I want to talk about just the surroundings, I remove the charge of the system. If I have the electric field and I want to talk about the interaction with a specific charge, I just multiply by that charge. Well, now, and I can't remember if I have the animation, so I might just draw it in. Now I'm going to go here. We have a new relationship. That force is conservative. And so there is a new relationship I can write here. Okay. That gives me the interaction, or the interactions. So instead of force, I can talk about potential energy. And I'll give you the equation now. Okay. You say, where does this equation come from? Why is the equation this? Calculus. There's a fancy way of doing calculus. Well, okay. Don't be scared. But anytime you hear the word derivative, all it means is slope. Derivative is a very fancy way of saying I'm finding the slope. That's literally all it is. Right? So from a conceptual standpoint, when you do the derivative in calculus, you're just finding the slope of the graph. See, people that take calculus, they want you to be scared and think that they're really smart. So the next time you say, "Oh, I'm taking calculus," you go, "Yeah, I know how to do slopes." Right? That's how you know. Yeah, I know how to do slopes. So really, this is how, I mean, this is how calculus does it, is they're just finding the slope. This equation, it'll look very similar, unfortunately, to this equation. It is going to be K, Q, big Q, little q, over R. So instead of being R squared, like the Coulomb force, it is just R. Unfortunately, it looks really similar. And indeed, if you take the slope of this potential, you will end up with that force. Yeah. So I'll put that in. I'll say, okay, if I have the potential to get the force, I just take the slope. If I have the force and I want to get the potential, you kind of remember what the opposite of doing a slope is? I'm just curious. Area underneath the curve. Does that sound familiar? You done? If I have the velocity versus time graph and I want to get the position versus time graph, I have to find the area beneath the curve. You look terrified, which tells me that you've done it.
This just reminds me of high school.
Oh, okay. Okay. Does that ring a bell? If you have the velocity versus time graph and you want to find the position versus time graph, you look at the area beneath the curve. Or let's do this. Or yeah, let's say I have the V versus T graph. T. Let's do this. There we go. And I want to get the position. If I know the velocity and I know the time, how do I get the position? Forget about the graph for a second. You're driving home to your house. You drive at 60 miles an hour for 3 hours. How far have you gone? 60 miles an hour for 3 hours. How far? 180 miles, right? You took how fast you were going, your speed, you multiplied by your time, and that told you your total distance. Of course, after 1 hour, you've only gone 60 miles. After 2 hours, you've gone 120. After 3, 180, yada, yada, yada. You notice you just took the distance in the x direction and multiplied by the distance in the y direction. You just took your total time of 3 hours and multiplied by 60 miles per hour. That gives you the area of the rectangle. So if you don't want to find if you want to undo the slope, if you will, what you have to do is you have to find the area. I'll put area here. This, so I'll put in reminder here. This is du over the change in u over the change in r gives you the force. What you'd have to do here is take your force and multiply by your displacement, which looks a lot like work. Units? Remember the units of this? Quick, what are the units of energy? Joules. This is in joules, don't forget. It's always good to remind you. For completeness, I'll put that in parentheses here. This is in joules. Advantages. The biggest advantage I can think of why I prefer not to work in forces and why I prefer to work in energy. You probably see it too. What's the pain in the rear thing about forces? Vectors. Probably your least favorite thing about forces is probably vectors. I'm hazarding. I hazard to guess that you hate having to worry about vectors. I just want to take two numbers and add them together. I don't want to have to Pythagorean theorem the sucker. I just want to take my two numbers and add them together. I don't want to have to find angles, add by components, and then Pythagorean theorem. I just want to add. Okay. Well, that's fine. You can just add. But you can't work in forces. You have to work in scalars, energy. So the advantage to going here is no longer do you have to worry about components. No longer do you have to worry about the vector nature of forces, because energy is not a vector, it is a scalar. So that's I think the main advantage, is that you can completely ignore the vector nature of forces. You can just work in terms of energy instead. What that means, what is it? Well, instead of looking at the vector field, you're looking at the topographical map. That's literally the analogy. Instead of looking at the vector field, all of the arrows pointing in every direction, you're looking at the underlying topographical map. Those two convey the exact same information. Choose the one that makes your life easier. Lastly, man, it would be really nice if there were some analog to the electric field. Right? Over here, I have vectors, forces, and down here I have a scalar. It would be really nice if I could write something right here that is a scalar that I can use to determine what the electric field is, so that I don't have to worry about vectors anymore. And of course there is. And in fact, you can probably tell me what the equation is. If you look at the pattern that's being followed, both going back and forth across the top and up and down, you can probably already tell me what equation I should write in this lower right-hand corner. What should I write? K, what was capital Q divided by R. Right? Because to go left and right, to go from left to right, I should remove my charge of my system. So let me get rid of that. And so to go this way, I just get that. Or if you prefer to go from top to bottom, you notice basically what you did is remove an R from the denominator. You get here. Quick, what's the units of this thing? What units should I write here? Just based on what we have up here on the board. Joules per coulomb, right? I take a joule, I remove a coulomb, so I should have something like joules per coulomb.
We change the units of measure that
I'm sorry?
we change the units of measure that we plug.
We change the units of measure. No, everything's still in SI. Or is that what you're asking?
Yeah.
Yeah, everything's in SI. Yeah. System international. Coulombs, meters, same thing that we've always been using. Of course, I don't know why we call a joule per coulomb something different. I mean, it's still a joule per coulomb, we just relabel it. That is known as a volt. It is the energy per unit charge. And we call this mystery quantity here is labeled V. It is called the electric potential. It is a scalar quantity, the slope of which will tell us the electric field. So again, we no longer have to work in vectors. We can think of the underlying topographical map and deal in scalars. Hey, thanks for your attention. That's all I have. We'll pick up there on Wednesday. But you'll use this idea. Incidentally, you don't have lab tomorrow, but this idea you'll use in lab on next week, next Tuesday. You don't have lab. I'll email everybody because Leo was asking me, hey, when are you guys going to talk about electric potential? I was like, well, we're going to start doing it today, but we're not going to get all the way through it, yada, yada, yada. So, yep, so I'll email you, but yeah, you don't have lab tomorrow. This will be lab next week.
Have a good one.
I lost class and stay at 2:30, so I should